Hello and welcome to Dr. Logic awkwardly does logic in her office. In this video, I'm going to introduce the rule of uniform substitution as it occurs in normal modal logics. I will define some notation, and then I will give you proof of the soundness of this rule, along with an example of how exactly this proof method works, because it's a little bit confusing in the abstract, hopefully less confusing after I've given you an example. So let me bring up my whiteboard. There we are. So I can give you the statements of the rule and the notation. Basically, the rule says that if you have a theorem, so if you've got a line written down in your proof, then the result of replacing all of the atoms with some well-formed formula and doing this replacement uniformly across the entire formula is itself a theorem. So, for instance, if I write down in my proof, necessarily P implies Q implies necessarily P implies necessarily Q. This is our K axiom. Then I can write down a substituted version of this. Oops, I lost my pointer. Nope, I still don't have my pointer. There we go. So, for instance, I could replace the P's with R's and the Q's with S's so that I have necessarily R implies S implies necessarily R implies necessarily S. So the annotation for this would be uniform substitution, and I'm doing it on line 1, and then you just want to say what formulas are you substituting for which atoms. So in this case, I've substituted R for P and S for Q. Now, in this case, I substituted atoms for atoms, but R and S could themselves have been complex formulas. That would have been okay. But that's what the rule of uniform substitution is, and I'm just going to give you a little bit of notation. So suppose that we have a formula phi, and then we've got these complex or possibly complex formulas, beta 1 to beta n, and atoms P1 to Pn. Now, these atoms all occur in this formula. Possibly other atoms do, but we don't care about them. We only care about the ones that we are stating explicitly. So the result of doing substitution, we can either write as beta 1 to beta n slash P1 to Pn, or we can pair them up individually so that we can say, well, I take beta 1 and I replace P1 with it, and I do this all the way up so that Pn gets replaced by beta n. So this is just notation, and you can see that we make use of this notation when we're writing down our justification for the use of the rule. That's the rule. That's how to write it down. The way that you can read one of these formulas is something like the result of replacing P1 to Pn with beta 1 to beta n in formula phi. Now, the next thing I want to do is prove to you that this rule is sound. That is, it is validity preserving. So we want to show that if phi is valid, then any substitution instance of it, so I'll just use this notation for now, is also going to be valid. That's what we need to show. Now, normally what we would do is we would assume the antecedent and the negation of the consequent, try to come up with a contradiction. But I'm not even going to worry about assuming the antecedent. I'm going to just directly show that if I can come up with a model that makes the substituted formula false, then I can construct a model that makes the original formula false. So if I have a model that makes the substituted formula false, then I can construct a model that makes the original formula false. So how do we do this? Let me clear the screen so that we've got a bit more space to work. So suppose that this formula, the result of replacing P1 to Pn with beta 1 to beta n in formula phi, is not valid. Then this means there is a model, call it M, and the world, call it W, such that the formula is false at that world in that model. Now, we don't know anything else about this model. We don't know how many worlds it has. We don't know what the relations are. We don't know what the valuation is. All we know is that this model has a world that makes the substituted formula false. However, that's all I need to know to be able to construct a new model that makes the original formula false. So we construct a new model, M prime, from the original model M. M prime is exactly like M, except for the valuation. So the frame, the set of worlds and the relationships between them doesn't change. Only the valuation change. So our new valuation is going to be called V prime, and we will define it as follows. Defined as follows. For every one of these atoms that we substituted a formula in for, so for every pi, or I between 1 to n, we will say that the value on this new valuation V prime of pi at world W is true if in the original model beta I was true at W, and V prime says that pi is false at W if back in the original model beta I was not true. For every other world, the valuation is exactly the same as in the original model, and for every other atom at Q, the valuation doesn't matter. So for every other atom Q, V prime is arbitrary, it does not matter. For every other world, V prime just is identical to B. So the only thing that we are changing is what value the atoms get at world W. Then, on this model, at world W, the initial formula will be false as well. So what we can show is that if we have a model that makes the substituted formula false, we can construct a model that makes the original formula false, so phi is not actually valid. This is the general method, and it may seem a little bit confusing because, as I said, we don't know anything about M, the original model, other than that it has a world that makes this formula false. But let me go through an example, and hopefully that will make it a bit more clear how this method is supposed to work. So let's clear the board and consider the formula P implies Q, and then the substitution instance where we take not R and substitute it in for P, and necessarily S or V, and substitute that in, for Q. So this formula then is not R implies necessarily S or P. what I want to say is that if you give me a model that makes this formula false, I can give you a model that makes the original one false. So let M be defined as follows. So just remember, M is a triple, the set of worlds, the set of relations, and the valuation. So W is going to have two worlds in it, W and W prime. R is going to relate W to W prime. And V is such that the value of R at the first world, at world W, is the same as the value of S at W prime and the same as P at W prime. They're all going to be false, and everything else is arbitrary. So it doesn't matter what they are. Let me draw you a diagram so that you can see what this looks like. Here we have W. It can see W prime. R is false at W. P is false at W prime. S is false at W prime. So from this, we know that S or P is false because both disjuncts are false. We also know that at W, not R is true because R is false. If this disjunction is false at W prime and W sees W prime, then we know that necessary S or P also has to be false at W. So this is a model that makes, by these two things, makes this formula false at W. We have a true antecedent, not R is true, and a false consequent, necessarily S or P is false. Now, we want to construct a new model, M prime, where, so M prime is going to be, again, a triple, W prime, R prime, V prime. The set of worlds isn't going to change. W prime just is W. Which worlds are related isn't going to change. R prime is just R. But then we need to say what V prime looks like. This, let's bring it out here so we've got a bit more space. We're going to say that the value V prime of P at W will be true if in the original model at world W, the formula that we substituted in for P was true. So if not R is true, and then we will say that the value of P at W is false if not R is false at the world in the original model. Then we say the same thing for Q. So what value does Q get at world W? Well, it will be true if in the original model, the formula that was substituted in for it is true. So that's necessarily S or P. Correspondingly, it will be false at W if it was not true at W in the original model. And then let's just put in here, everything else arbitrary. It doesn't matter. The only atoms that we are interested in changing the valuation of is P and Q at world W. Everything else, we can just say, let it be the same as V, just that, so long as we have changed this. So now, the model that we have is built on the same frame. So we've got W and W prime, and W sees W prime. So now, we want to know what value does P get at W? Well, it gets true if in the original model not R was true, which is the case. So P is true. What value does Q get? Q gets whatever value necessary S or P got in the original model, and it got false. So here, Q is false. Now, what do we have? P implies Q is also going to be false. So this model makes the formula that we started off false and therefore invalid. So given a model that made the substitution instance invalid, I was able to construct a model that made the original formula invalid. Therefore, take the contrapositive. If the original formula is valid, then the substituted formula has to be valid as well. There would be no way that I could make this construction. So I hope that this helps you see how the rule of substitution works and why it works, why this is a truth-preserving rule. In any case, I hope to see you again soon. Take care. Cheers.